Okay, so today we are going to be talking about nuclear physics. So, quick definition, nuclear physics is simply the study of the interaction between the nuclei of atoms. Okay, so first off, we're going to define some important terms. Now, I'm assuming you understand our current model of the atom involving what a proton is, what a neutron is, and what an electron is. But some new terms that are important to this video are nucleons. Nucleons are just the particles of the nucleus. So that means neutrons and protons. So when you refer to an atom, if I were to ask the total number of nucleons in an atom, it would be the sum of the protons and the neutrons. Another important word is isotope. An isotope is a different version of an element with a different number of neutrons. Remember, elements are defined by the number of protons in an atom. So every atom of hydrogen will always have one proton, every atom of helium will always have two protons, and so forth. And so, obviously here we have hydrogen with one proton, no neutron. That's called protium. Then you have deuterium with one proton and one neutron. Then you have tritium with one proton, two neutrons. But that's always hydrogen, just a different number of protons, different number of neutrons. So another important thing we need to define are alpha and beta particles. Alpha particles consist of two protons and two neutrons. Because of this, they're identical to a helium nucleus, and all alpha particles compared to beta particles have a relatively high mass, and they have a charge of 2 plus because they have two protons and no electrons. We also have beta particles, which consist of either one electron or one positron. They have extremely low mass, and if it's an electron, has a charge of if it's a positron, it has a charge of +1, or if it's an electron, it has a charge of -1. So first off, we're going to talk about an early model of the atom. This is called the Plum pudding model, and it was proposed by J.J. Thomson in the late 1800s. It's important to note that this is completely wrong, but it was an early model. It's important to know what it was. So this model stated that electrons existed in the atom, and they were surrounded by a sea of positively charged material. That's where the name plum pudding comes from, because it kind of would look like plum pudding. As I said, proposed by J.J. Thomson, is now wrong. In response to this, Rutherford wanted to test the legitimacy of this experiment, and he had two of his assistants, Geiger and Marsden, who was also, this experiment's called both the Rutherford's gold foil experiment and the Geiger-Marsden experiment because of that. So in this experiment, they had a sheet of foil, and they just simply launched alpha particles from a source into the gold foil. And what they expected to happen is so there'd be a very small deflection, because after all, electrons have very small mass, so there'd be nothing big enough in the gold foil, in each one of those atoms, to actually deflect the alpha particles. However, although still most of them went pretty straight, some of them deflected at extremely large angles, which made them consider the fact that perhaps there was something with a greater mass within an atom, and that's where the model of the nucleus came from. Oopsie. So, the Rutherford model proposed that there is a nucleus composed of protons and neutrons, and this is surrounded by orbits of electrons. One major limitation of the Rutherford model was that it can't really explain why the electrons would stay in orbit around the nucleus, because after all, one would think that they would lose energy over time and eventually would come into the nucleus. Another thing it can't explain is it cannot explain why the nucleus stays together, because after all, protons have positive charge and neutrons have no charge, so why would protons stay bundled together in a nucleus rather than repelling each other? So next we're going to talk about alpha decay. Alpha decay is when a nucleus emits an alpha particle, as you might guess. So in alpha decay, the nucleus will get rid of two protons and two neutrons. So in total, 4 nucleons will be lost. So in our example, we have we have radium at the beginning, radium which has 88 protons and 222 total nucleons, and then emits an alpha particle, which can be written as helium, and then plus 208 with radon, which has 86 protons and 218 nucleons. So when you're solving these problems, it's the two things you have to keep in mind is the number of nucleons has to stay constant, and you can check that by, so top row, we know on one side of the equation we have 222 nucleons. Right side, we have 4 nucleons plus 218 nucleons. So obviously that adds up to 222. We're all good. The number of nucleons is the same on both sides of the equation. Same thing, on the bottom, you have to keep the total charge the same. So on the bottom, we know we have 88 protons on the left side of the equation. On the right side, we know we have 2 protons. 2 protons plus 86, so 88 protons. And we're not worried about electrons, so we know there's the same amount of protons and no different amount of electrons. So we know we're still safe when it comes to charge. Now we're going to talk about beta minus decay. In beta minus decay, a nucleus releases an electron, so 1 neutron in the nucleus is turned into a proton. And also you want to memorize that an antineutrino is also emitted. So here you can see we have carbon 14, and all that means is you have a carbon with 6 protons with 8 neutrons. That's an isotope of carbon. And then through beta decay, it turns into nitrogen 14, so with 7 protons, 7 neutrons, plus an antineutrino, plus an electron. So what's going on is the carbon 14 releases an electron. So when it releases an electron, you know that one of the neutrons will turn into a proton. So the proton number will increase by 1, and the neutron number will decrease by 1. And then and as I said, an antineutrino is also released. So check and make sure this equation that we have written here makes sense. We know that the number of nucleons, 14 on the left, 14 on the right, is the same. And then we check, make sure the charge is the same. So on the left, we see we have 6 protons, and on the right, we have 7 protons. So, oh no, it's not balanced, but wait, there's an electron also there. So the electron explains what this equation is balanced, because 7 minus 1 is 6. So right is 6, left is 6, we're all good. Next, we're going to talk about beta plus decay. So here we have a nucleus releases a positron, converting a neutron into a proton. So here we go. So as I said, you can see we have carbon 10 on the left, boron 10 on the right. You can see that the number of protons changes because one of the nucleus releases a positron, so one of those protons turns into a neutron. So now we will go from 6 to 5 protons, and from 4 neutrons to 5 neutrons. So we're going to check. We have the same number of nucleons, 10 on both sides. We have 6 protons on the left, only 5 on the right, but the positron gives us an extra charge. We have a charge of 6, plus 6 on the left, and plus 6 on the right, so we're all good. And as I said, same number of nucleons in total. So that concludes this video on nuclear physics. Thank you.